I've given everyone colored pencils so you can do the same color coding. Folks, I'm not going to lie, I first taught this course in fall of 2020, and I hadn't done any triple integrals for about 15 years. So I had to reteach myself how to do this. This is what I did to be able to get to the point where I could teach these topics. Okay? I just worked several problems where I worked all possible directions and worked a number of these examples. So let's just do this together, see how this works out. Okay? So let's first integrate. First we'll do the integral. And what I recommend doing, sorry folks, before I got started, give yourself some space here to be able to write, equations. F of x, y, z. And we're going to do the order dz, dy, dx first. Now, this is going to restrict us. I wish I had one more color to give you. I apologize I don't. Maybe you've got a pencil or something. Maybe you've got a pencil here to use as a different color. So the domain that I'm pulling, the way you think about iterated integrals is, once you've learned what a double integral is, you can nest them as deep as you want. I think of my domain as taking a point from the xy plane. Once I've selected a point from the xy plane, I'm going to let my z vary as I move through this surface. Okay? So in this problem, I'm restricting myself to the xy plane. Okay? Does that make sense there, folks? So we're going to be looking at, what we're going to do is we're going to project, now this part's not very exciting in this problem. I'm going to project the entire 3D solid into the xy plane. Andrew's got a soda can there. If you were to project that into the xy plane, maybe it's Gabe, I'm not sure, you stomp on it, right? Projecting it into the xy plane. Okay? Next time you guys are stomping down soda cans, you can think of Calc 3, projecting into the xy plane. Okay? So if I were to take this whole surface and project it into the xy plane, what it gives me is this region right here. Does everyone see that? That's what I do in a pencil, or something other than the colors we'll use for picking points. Does that make sense? Now, what's kind of dull about this problem that leads students to misunderstand how hard these are? In this case, the projection into the xy plane is no different than the trace of the xy plane. So it's hard to explain to people what we're doing. Don't worry, we're going to ratchet up the level of difficulty, and eventually we'll be projecting into the yz plane, and you'll have a better sense of what I mean by that. Okay? So the first thing we're going to do is, because we're integrating in the dx, dy, dz order, we're integrating in the dz, dy, dx order, but when we go to set up our limits of integration, we're working outside in. Okay? So we're going to do from x equals, and I can take x values all the way between here and here, right? So we're going to go from x equals 0 up to x equals 1. By the way, if you don't like this idea, especially if your image gets too messy right here, what I normally do when I don't have all these images drawn for me is here's x, here's y, and then here is my purple projection into the xy plane. Everyone see that? So this is actually, so somebody asked me the other day, I think it was Josiah who's out today, Josiah asked, do you always need to be able to draw this whole solid? And to some degree, like, I try to do a rough sketch of a solid as I'm doing these when I can, but what I do always sketch is the projection into the domain plane. Okay? So I always have this part, because that's the part where I say make sure you've got an image to work with, make sure you draw your region. Okay? So I'm picking x coordinates between 0 and 1, and then what am I going to do? Well, I'm going to let my y coordinates vary until as I move through that region, right? So I'm going to let my y coordinates vary, and no matter where I do that, do you see what my y coordinates always do? I'm not going to do y from 0 to 1. If I did y from 0 to 1, it would give me this box here as my region, not the triangle. So I'm going to go from y equals 0 until I hit this curve right here. In this case, this curve right here is the intersection. Well, it's many things, I guess. The easiest way to see it is that's just the line y equals x plus y equals 1. Okay, lots of ways to see that. So that's y equals x plus y equals 1. So then if we solve that for y, we get y equals 1 minus x. How's that working, folks? By the way, sometimes what you'll see in my drawings, because like what I like to emphasize, I'll put that right back. What I like to emphasize is that I'm going out to a specific set of points. Let's see here. So what I'll do instead, just to explain my drawings that you'll see in the keys, is I draw it like solid and then I keep dashing it to where I stop. Something like that. There's lots of ways you can think about that. So I don't want to, and my notation is not always consistent throughout. But that way I think about going, x is at this value right here, and then I'm going to let y vary until we get to here, and then I'm going to let my z vary. Okay. Sometimes, though, I use the dashed line to show that I haven't yet gotten into the region, so just be careful there because I do change the notation on that. Okay. So going back. So then, once we've selected, this is how I get systematically through my domain. All you need to think about is like, wait, I need to take, to evaluate a triple integral, I take every point in the solid and plug it into the function, right? And so the iterated integrals are just, one way to think about it is just a systematic way to make sure you take all points in your solid region. So once I've got an x, y ordered pair, I'm now going to let z vary up until when we hit that plane. Okay. So z is going to go from 0 till we hit that plane up there. What's that plane? That's this plane, z equals x. Okay. How we doing, folks? So usually, if I've already done the work to do one iterated integral, and all I do is swap the domain one, it's usually not that hard of a problem to do. So let's do that one next. We'll do the integral and the integral of our f of x, y, z, and let's do the order dz, dx, dy. Okay. In this case, I'm going to think about taking y coordinates between 0 and 1. Okay. Again, folks, don't try to, if you're changing the order of integration, don't try to just think about, oh, how can I just move these things around? You really do have to sketch your region, at least your domain region, to be able to do that. You cannot just start moving these pieces in the limits of integration around. That may work for 1 or 2 or 10 problems. It will not work for all, and it's not the correct way to do it. And eventually I will find a problem that you completely missed because you've done it that way. Okay. So in this case, we're going to go from y equals 0 to y equals 1. Then we're going to go from x equals 0 until x hits that line, which is now the line y minus 1. Okay. Remember that when I'm moving through this, I'm taking different x values until I hit the boundary of that plane right there. Okay. The boundary of that plane, this was the plane x plus y equals 1.
Isn't it y minus, 1 minus y?
1 minus y, yes, thank you. I should have written it. I should have written that part out and then said solve that. I was about to say that. Then you solve this for x, and you would have had 1 minus y, which I didn't quite get to. Okay, how are we doing, folks? Okay. Then I'm going to pick a z coordinate, and this part is always going to. Do you notice that this part's always going to be the same? Because I've gotten the same x, y ordered pairs, and then I just allow z to vary. So if all I do is rotate out these two, that's not going to change this expression here. So this is going to give me z equals 0 to z equals x. How are we doing, folks? Okay. Let's make it a little bit harder. Okay. So now let's do the order. Let me write it up here. Don't write the order until I've double checked that it's the one I want. I always get this part. I always have a hard time with this. Let's see here. f of x, y, z, and we want to do d, and then we'll do dz dx. Okay. So in this case, I'm going to go from allow x to vary from x equals 0 to x equals 1. My domain is this dz dx region. And the way I think about it is taking, folks, if my domain is dz dx, what am I going to do? I'm going to project the entire solid into the dz dx plane, or the dx dz plane. So I'm going to take the solid and smash it in there, and that would give me this solid right here. Again, why is this a little bit misleading? Because it was already the footprint is the same as the trace. The projection is the same as the trace, and that's not always going to be the case. Okay? So once I've picked an x, I'm going to allow z to vary until we hit here, right? Oops, I'm sorry, folks, I want to do that in green just to stay consistent. Green second. How are we doing? So we're going to go from z equals 0 up until we hit this plane right here. What is this face? This plane, this face right here, this plane right here, or this line right here, when we project the whole surface into the xz plane, is the plane z equals x. Okay. Then we're going to allow y to vary. So y is going to go from 0 up until we hit this face, which is the face 1 minus x. So we're going until we hit, don't write this down, I'll make your image too cluttered. I'm going until I hit that outer face of this region. Okay. Now, folks, I will tell you, by the time we're done with this, we will have done what I think of as a medium level problem for these. Okay. There are definitely harder ones, because it becomes harder to come up with what is it exactly that I'm intersecting. That's where that gets harder. Okay, so this is about a medium level problem. Okay. But if you can do this one, you at least know the process for doing those harder ones. Okay, so folks, changing the script here and doing the integral, just changing the domain plane, so we still have f of x, y, z, dy, then now this is dx, dz. That doesn't make things all that much more difficult. So notice specifically, even though I normally do these in this order, this is still going to be from y equals 0 to y equals x minus 1. Okay. But let's go ahead and set this up. We're going to let z vary between 0 and 1. But this is our first one, and here's the first time these have gotten a little bit more interesting as far as the regions go. I need to then I'm taking these points here, right, from the xz plane. I'm taking that face back there, that's my projection, into the xz plane. Again, folks, normally that gets a little bit messy to try to draw. So normally what I do instead is I actually write here's positive x, here's positive z, here's that projection right here. Okay, so folks, this is our first time. If you're looking at this, we took a z coordinate, and now we're going to take an x coordinate. Well, I don't start getting x coordinates until I enter this purple region. Let me try to make that a little bit easier to see. So in this case, I'm going to put dots there like so. And I'm trying to show you that I don't start getting x coordinates until I enter the purple region. Those are going to be my x, z ordered pairs that are my domain. So this is going to be from x equals z up until x equals 1. And this is the first time where if you were just flip-flopping things around, you realize, oh shoot, that's the wrong way to think about this. Does everyone see that? Anyone have any questions on this part? It's absolutely essential if you have a question right now that you ask.
Why is z on the bottom integral? X equals z on the bottom.
So what is this? What is this line right here? Let me do it in. It's going to be a little messy with colors, but this line right here is which line?
X equals z.
That's the line x equals z.
Oh.
And this line right here is which line? This is the line x equals 1. When did I start collecting x coordinates? When I passed the
X equals Z.
orange line, and I stopped when I hit the yellow line. Great question.
Thank you.
Once I've got, so in this case what we have is we didn't take any points until we entered. And once I've got an xz ordered pair for my domain, or in this case it would actually be zx is the order of the ordered pair, a zx ordered pair, I then, we're going to go from y equals 0 up until we hit the y equals 1 minus x. Okay, how we doing, folks? Yeah.
So with the same projection as the previous one, number 2, like,
Yeah, I'm sorry, I'm not going in numerical order. 2 and 5 have the same projections. Yeah, so 1 and 2 have the same projections. 2 and 5 have the same projections. It's just technically, though, you know, sometimes what I'll do here is I'll actually rotate this again, because I like to think of this is my independent axis, this is my dependent axis in the plane, and those have technically switched between the two. Yeah. All right, the last two. In my opinion, this is where it gets a little bit harder. So let's go ahead and do our order as dx, dz, dy, dx, dz, dy. So in this case, I'm going to project into which plane, folks? The YZ plane, right? So I'm going to take this whole surface and smash it into the YZ plane here. When I do so, this right here will be my projected surface. Does everyone see that? Using my analogy of taking a solid and stomping on it to make it flat, we're going to be stomping along the x-axis here to smash this whole surface to project it into the YZ plane. Okay. To be honest, once we've done that, that's about the hardest part. The last thing we need to do is identify what's this curve right here, and this one's a little bit different. This part is a little bit harder here. This right here, this boundary is, what caused that boundary to be formed? What part of the projection caused that boundary to be formed? Do you all see it? It is this piece right here. That piece right there created this boundary right here. Does everyone see that? Here, because here's the thing. I don't have a description of this already in the YZ plane. I have to come up with it. And what we realize is that line is the intersection of the plane x equals z and x plus y equals 1. It's the intersection of those two. Do you see that? So this boundary right here is formed by the smashing of these two faces. This face right here and this face right here. Do you see it? That's where that came from. The green one is the plane x plus y equals 1. The blue one is the plane z equals y. So I'm looking, oh, sorry, x equals z or z equals x. I'm sorry. Thank you, thank you. Okay. So it's this plane and this plane. This one's blue. This one's green as I've drawn them here. Okay. So points that are along this purple line are where? They're on both planes, right? It's the intersection of the two. So I'm going to solve this equation for y and z. Solve that system of equations for y and z. So I'll take that part out because that's just a little bit too ugly to look at. All right. So this happens when z plus y equals 1. Everyone see what I did there? I mean, it's almost too easy of a substitution. What is x? It's z. So I took the equation x plus y equals 1 and I plugged in a z there, right? Okay. So that boundary is the line z plus y equals 1. Once I've identified that, I'm basically back to where I've started from. Okay. So the first thing I'll do is I'm going to let y vary between 0 and 1. Then I'm going to let z vary. Everyone notice where I'm drawing my z strips, those variants of z. Once I pick a y coordinate, I allow z vary as I go through that purple projected region. Okay. So that's going to go between z equals 0 and z is equal to 1 minus y. And you can see where a student who's struggling with this will start looking for patterns amongst these values that aren't really what's going on here. You're not looking at patterns up here versus patterns down here. It gets you into trouble. The correct way to do it is to draw the region. Okay? And that's also where MyMathLab has a really hard time teaching you this, right? Because it doesn't draw regions very well. Okay? Once I've picked one of these, I'm going to let x vary until I hit this face and stop when I hit this face. So that's going to go from x equals, what face is that? That's the plane x equals z. And we're going to stop when we hit this face, which is the plane x equals 1 minus y. Thank you. Okay. And again, this is where if you didn't do all 5 or 6 of these, you started to think that you had this down without realizing just how messy these could potentially get. Okay. Let's do the last one real quick. So this will be dx, dy, dz. So z is going to go between 0 and 1. Y is going to go between 0 and 1 minus z. I should make that bigger. And then x is going to go between, that part doesn't change, so x is going to go between z and 1 minus y. But if you go back to our 16.4 notes, the very end, I've got this one here where you do the same thing. This one's a little bit more challenging because just working with parabolas and radicals and stuff like that. Okay? And I recommend, if you haven't done this, go through this one. I'm sorry the video is a little bit rough.